Welcome to Simple Linear Regression, Part 1. Simple linear regression forms the foundation of predictive modeling, and in this video I'll walk you through the basic steps of one way to perform regression analysis. Other simple linear regression methods may give you a more informative output or offer more features. This video demonstrates the use of the LM function, and LM in this case stands for linear model. Simple linear regression attempts to find a model, basically an equation, that describes the relationship between one dependent quantitative variable and one independent quantitative variable. When we have more than one independent variable, the analysis is called multiple regression. One of the main goals of regression analysis is to be able to predict the value of the dependent variable based on the value of the independent variable. Another goal is to interpret the meaning of the regression coefficients. Linear regression is based on several assumptions. One assumption is that there is a linear or straight line relationship between the variables. A scatter diagram and other graphs can help validate the linear assumption. And if the relationship does not look linear, another model might be preferred. Another assumption is that the scatter above and below the regression line is independently random and normally distributed. A third assumption is that the scatter around the line is uniform along the line. This means the data points do not funnel in or fan out as you look along the line from left to right. Another assumption is that we have a sample of data that has been randomly selected from the population. Now, some models are useful, but all models are wrong. And one reason they may be wrong is because some of the assumptions are not perfectly met. You may recall the equation for a straight line, y equals a plus b times x, where a is the intercept, the point where the line crosses the y-axis, and b is the slope, the change in y when x increases by 1 unit. The population regression model says that the mean value of y in the population is equal to an intercept plus the slope times x. By convention, the population intercept is called beta naught, and the slope is called beta 1. When we describe the sample regression line, the intercept is called b naught, and the slope is called b1. By the way, b0 and b1 are called the least squares estimates. This example uses the MT-CARS dataset from the datasets package. This package comes with what's called base R, which means that it's automatically available when you start R, so you don't have to load it or install it. In this example, I'm using two variables from the MT-CARS dataset, MPG, which is miles per gallon, and DISP, which is indigent displacement in cubic inches. To keep the code simpler, I used the $ operator to tell R that DISP and MPG were both in the MT-CARS dataset by creating two new variables and naming the new variables DISP and MPG. The plot function creates a scatter plot. The first argument, DISP, is the independent variable. It's shown along the x-axis, and the second argument, MPG, is the dependent variable. It's shown on the y-axis. Showing the independent variable on the x-axis is the convention in most scientific fields. The PCH equals 19 argument tells R to use small black circles for the data points. The PCH argument controls how the data points will be displayed. If you do an internet search on how to use PCH in R, you'll get quite a few hits. And by the way, that's a good way to get answers to your questions about how to do something in R. The AB line function adds a regression line to the plot. The LM MPG tilde DISP function tells the computer that MPG is the dependent variable and that DISP is the independent variable. The color red makes the line red, and LWD equals 2 makes the line twice as wide as normal. Here's the line, and you can see that there's a negative relationship between engine displacement and MPG, as you would expect. The data points look pretty uniformly scattered around the line. You may notice a slight nonlinear pattern when the displacement is lower than about 160 cubic inches. This slope looks a little bit more negative, but on the whole, it looks like the regression assumptions have been reasonably met. We use the LM function to find the least squares regression model. The first line of code creates an object. In this example, the object is named model. Any valid variable name can be used. It cannot start with a number, and it cannot contain a mathematical operator such as a dash, that's a minus sign, or /, that's for division. Names can contain periods and underscores. An object in R can be thought of as a vessel that contains information. In this case, the object named model will contain the results of the regression analysis. The right-hand side tells R to use a linear model. The first argument in the LM function is always the dependent variable, MPG in this case, and the value after the tilde, found in the upper left on most keyboards, is the independent variable. The data equals argument tells the computer where to find the data. On the next line, the summary function prints a summary of the regression analysis. The first part of the summary output displays the call. It tells you that LM has been used, and it shows the variables in the data set that is used. The output shows a summary of the residuals, which are the vertical differences between the data points in the regression line. Below that, you see the regression coefficients. The sample intercept is 29.6 rounded, and the sample slope is negative 0.04 rounded. In most regression problems, the intercept is not very informative, but it's necessary in the regression formula to be able to predict y. The intercept is where the regression line crosses the y-axis. In this case, it's the average miles per gallon when displacement equals 0. Now, this makes no practical sense because you can't have an engine with 0 displacement, but it needs to be in the formula to calculate the miles per gallon. The standard errors of the regression coefficients are standard deviations of the sampling distribution of the regression coefficients. The t-values are the coefficients divided by their standard errors. And the p-values help you evaluate the significance of the coefficient. Smaller p-values suggest the variable is important. A common decision rule is to use 0.05 as a cut point. If the p-value is greater than 0.05, you may not want to use that variable in the model. In this case, the p-value is very small, so displacement would be viewed as useful when predicting miles per gallon. The output contains a statistic that's labeled multiple r squared. Since we only have one independent variable in this example, this is actually the simple r squared. R squared is called the coefficient of determination, and it's an important statistic. One way to think about regression analysis is to ask yourself the question, why don't all the cars get the same mileage? Why do some cars get better mileage and other cars get worse? R squared measures the proportion of the variation in miles per gallon that's explained by the model. In this example, displacement explains 71.8% of the variation in miles per gallon. R squared ranges from 0 to 1, and higher values suggest a better model. The ANOVA model code creates what's called an analysis of variance table. I'm focusing on the sum of squares column. We see that DISP has 808.89 sum of squares, and the residuals have 317.16 sum of squares. When we add these, we find that the total sum of squares equals 1126.05. So there are three different sums of squares. The symbols used for sums of squares vary sometimes from one textbook to another, but the symbols I'm using are pretty common. At the top of this slide is SSR. SSR is the sum of squares explained by the regression model, and this equals 808.16. Next is SSE. This is the error sum of squares. It equals the sum of the squared residuals, the distances, vertical distances, between the data points in the regression line. This is the unexplained sum of squares. When these two sum of squares are added, the sum equals the total sum of squares. One way to calculate r squared is to divide the explained sum of squares by the total sum of squares to find the proportion of total variation that's explained by the regression model. And in this case, once again, we find r squared equals 0.718. We can use the regression model to predict miles per gallon for a new observation. In this case, assume we have a new observation. a car with an engine that has displacement of 150 cubic inches. In the first line, we create a data frame that sets DISP to 150, and we put that in an object named new.data. In the next line, we use the predict function. The first argument is the model that contains the regression results, and the second argument is the object that contains the data frame. When we run these two lines, we find that y hat, the predicted miles per gallon for a car having a displacement of 150 cubic inches, equals 23.42 miles per gallon. Simple linear regression is the first predictive model we'll study. It's used to predict the value of y, the dependent variable, given a value of x, the independent variable. The LM function in R is a basic, easy-to-use way to get regression results. We'll be using this function for a variety of regression models. By itself, the simple regression model might be too unsophisticated to provide realistic predictions, but it forms a rich foundation that leads to other models. The simple model can be modified and expanded to handle more complex and realistic situations. That's simple linear regression in a nutshell. Thanks for watching.